Start recording. So here we are on session number the third. On session number the third. So what we're going to be talking today? We're going to be talking about declarative programming, which is, for the record, well, two things on the record. Last time I asked Marinho, what does it mean to say that a program is declarative? And Marinho couldn't really get me an answer, but this guy could. It was just a little bit late. Um, so there is this question.
Yeah,
Uh,
I forgot for a moment that this was actually asked in the book because I actually read this book a while back, right?
no, no, I'm not trying to shame you or anything because this is a 900 pages book. It's normal to forget the details of things. Uh, so I'm just saying that for last time I criticized the book by not being specific and precise about what the heck we're talking about.
Well,
Uh,
this is where it is actually specific and precise, I guess.
yeah, it was just late. Timing problem. Um, okay, so declarative programming, what it is actually. So we say that operation is declarative if it's independent, stateless, and deterministic. And that's a very interesting definition because this is basically saying that pure programs are declarative.
Which is
Right.
fair.
Um, but the reverse is the interesting question. Are all declarative programs pure then?
What do you mean by pure? That's the question.
Well, that's fair, but let's use the usual technical definition, which is um something along the lines of the referential transparency, controlled side effects, things like that. Because when you talk about that, usually we're saying that the operation doesn't depend on any execution of state outside of itself. It doesn't have to remember something from before, and it's the same inputs give you the same outputs.
Mm,
So like it's almost like the instead of talking about purity, these authors talk about declarativeness.
I guess the question will come down to, do you consider manipulating unbound variables to be part of pure programming? Because that's basically the difference between this model and a purely functional model, right?
Yeah, he's gonna say somewhere, I don't remember where anymore, that if you have a strict functional, a strict declarative language, you go into the Haskell territory, and then you cannot do constant time operations later on. You need the data flow variables to make that happen. Um, but anyway, that's just a like interesting thing I would say. But then let's go why declarative programming is important. We're not gonna read everything, just the highlights. So you can compose programs. So a declarative program consists of components that can be written, tested, and proved independently over the components of its own past history. That's because they are stateless. Reasoning about declarative program is simple. Um, and what the heck is a component? A delimited program fragment with well-defined inputs and outputs. So we're talking about procedures and functions.
Um, yeah.
Um, yeah, so essentially, purity all around. At some point here, he talks about referential transparency, which I already forgot where it is.
Yep.
Um, so everything that we've seen before in chapter 2, they are declarative. And then we're gonna go. Yeah, this is basically the summary of the chapter. So we're gonna start by asking this question, and then we're gonna go through iterative and recursive computation, and then programming with lists and trees. And I think actually that's what we're gonna discuss today. And then I believe the rest of the chapter, which is gonna be next time, we're gonna be talking about these other things.
Yeah, this is a very long chapter.
Yeah. So the first thing that is interesting, the first thing that is interesting is that in the declarative programming root, we have a branching here that separates descriptive from programmable. And descriptive, yeah, here it is, with racial transparency, right?
Yeah.
Which, well, for those not initiated, this essentially means that you can swap, you can do a substitution operation symbolically, and the semantics are preserved. So, for example, if you have this thing equals this thing, you can go to the places where this thing is happening and swap by this other thing. Um, and this is possible because FA is declarative. It depends only on its arguments and not on the other computation state. Um, well, I should also say, I never thought about this, but I have a feeling in my gut that this also assumes lexical scoping instead of dynamic scoping.
Well, dynamic scoping is computational state that is not actually part of the function,
I
right?
agree, but that's not written here. Because, like, I think that would be a pretty interesting insight. That, hey, um, this also assumes lexical scoping. Why? And then there's a footnote down here explaining why.
Yeah, that would be nice, but well, dynamic
Um,
scoping can be useful, but it shouldn't be the default, and the reason is this actually.
yeah, so another interesting point is that a recursive function is the one whose definition body refers to the function itself, either directly or indirectly. Direct recursion means that the function itself is used in the body. So this is what we would call self-reference. Indirect
Yep.
recursion means that the function refers to another function that directly or indirectly refers to the original function. So this definition is actually genius because it encompasses two other recursive cases, right? So because there are three ways of doing recursion. There is self-reference by itself, which is called indirect, and indirect encompasses the other two, which is mutually recursion and fixed point recursion. So this is pretty encompasses all of them in a single thing. So I think that's pretty great.
Yeah, not something people tend to talk about, but it's a useful distinction to make.
Yeah. So then we're gonna go to the descriptive declarativeness, and the first thing. Okay, guess what it was the first thing that came to my mind when I read this sentence.
JSON,
Better.
XML,
I'm not Magetta. Try again.
S expressions.
I'm not Magetta. Try again. Let's try.
It just defines a data structure, and it's not XML or S expressions or JSON.
5 seconds.
Uh, yeah, I don't know.
EDN.
Oh, EDN from Clojure, of
Yeah.
course.
So yeah. So this declarativeness definition encompasses data structures that we usually, well, such as what Marinho described, JSON, HTML, as the book says, XML, and EDN, which is the Clojure one. So that's pretty interesting because usually we don't talk about raw data structures as declarative programming, but they kind of are. That doesn't mean that all of them should be used, such as JSON, but they can. And then we have programmable declarativeness, which is essentially programming languages, right? In this case,
Yep.
it's saying that it is expressive to a machine, and then there we have the definitional view and the observational view of programmable declarativeness, which is another branch in our thingy. So observational and definitional. So what the heck does those words mean? What? declarativeness is a property of the component implementation. So if you're looking inside something, that's a definitional view. If you're looking from the outside behavior, or there is, we can use a component based on its specification only without knowing its implementation. That's observational.
Yeah,
Uh, and then we have two styles that are definitional declarative programming, so implementation wise, which is functional and logical. And we have Haskell and SML in one land and Prolog and Mercury on the other land. Um, and the observational view lets us use declarative components in declarative program even if they are written in a non-declarative model. Well, of course, right? Because you can have implement in specification-wise something that is declarative, but its implementation may not be declarative.
yeah.
The component just
Sometimes,
has to
yeah, sometimes
behave
it's
declarative. Go on.
yeah, sometimes it's usually it's for performance, right? Because you can
What
do
is
some.
the first thing that came to my mind? ST from Haskell. So when you have ST or any sort of like IOREF or STREF or whatever that is using some sort of explicit state, you can make the function implement in specification wise behave like it is independent, stateless, and deterministic, but its body is actually doing a bunch of mutation shit.
Actually, what comes to my mind is actually Clojure's collection functions, because Clojure has a notion called transient, which basically lets you create one of its immutable data structures, but in a mutable version. So you can very efficiently build up a large collection, and then you can turn it into an immutable version at the end, so you can use it normally.
Yeah, that means that's also a very good example. The reason that ST is the first thing that comes to my mind is because ST is the intuition that I have for it is to be in local mutation. So you need to do something, but the mutation and all the madness will happen within a very tiny scope. It doesn't have to spread everywhere. So you can make this the function signature seem like it's just a pure innocent naive function, but when you look at its implementation, it's doing a bunch of other stuff that you're not even aware of. And because it's in local, it means that it's also referentially transparent.
It wouldn't be, unfortunately, if you use the something like that in Scheme because of continuation capture.
Damn. Uh, okay, those are very good examples, Marie. The implementation of this interface is almost certainly not going to be logical and functional. Well, a database interface can be a valuable addition to the declarative language. It suffices that
Yeah,
it
they
could have been defined declarative.
yeah, the atomic comes to mind with the whole the database is a value idea, right?
Mm-hmm. Yeah. But we will not be dogmatic about the matter. We will consider the component to be declarative if it behaves declarative. So if they look like a duck and they walk like a duck, for us it's enough. Um, so specification languages. Um, and then proponents of declarative programming sometimes claim that it allows to dispense with this implementation since specification is all there is. That is true in a formal sense, but practically not really. Practically, declarative programs are very much like other programs. They require algorithms, data structures, structuring, reasoning about the order of operations. This is because declarative languages can only use mathematics that can be implemented efficiently. There is a trade-off between expressiveness and efficiency. Declarative programs are usually a lot longer than what a specification could be. So the distinction between specification and implementation still makes sense even for declarative programs.
Right. This goes back to the quote at the beginning of the chapter where they mention, okay, um, some specifications make for terrible programs because, like, if you just read the specification and translate it naively, it would be hella inefficient, right?
Yeah, I
There's
think that,
actually
but I
yeah,
think
there's
that's part of the like I would like to live in a world where we would have a magical box that picks my naive implementation and makes it efficient. That's
Yeah, that's
what.
called a that's called a sufficiently smart compiler, and it's the stuff of myth, you know.
Well, some we can make these compilers a little bit smarter than just like translation machines. They can notice patterns, they can rewrite patterns, they can optimize patterns. But we're not yet to the point that I can write completely like very hard to optimize, non-naive type to optimize program and make it efficient. So we have to care about actually even though this looks pretty, it cannot be implemented efficiently. So let's not do that.
I mean, there might be an efficient way to implement it. It just would be harder to specify that implementation, right? Because it
Mm-hmm.
needs to be more finicky.
Uh, yeah, so then we go through the whole thing about composing declarative components. I don't think we need to go over this. This is fine. And then this book does something that is really rare, which is to name, and that's the thing. I don't know what's the rule that these authors use to name stuff. I never seen accumulator programming before. That's weird. So are we gonna talk about identifier programming? Are we gonna talk about floating number programming? Like, what is the rule to name things?
I think it's about like this a particular style of programming because if you say okay, it's a floating point programming, like you're using a particular data type,
No, but
but that doesn't
if that's the case,
really.
like, you know,
But yeah, but like if you say floating point programming, okay, you're using a particular data type. What constraints does that impose on the structure of your code? You know, not many.
well, but that's the thing. I'm not. You can attach some meaning to it. I'm not saying that meaning is going to be useful or not. It's just that I'm not saying this is not useful. Okay, like the iterative computation thing and the accumulator pattern there, those are very useful things. Like I didn't read about them. I kind of I was taught to use them by I don't know professors and courses and maybe myself. I just like man, what if I do this this and this? Like I'm not a genius, but maybe this gonna work. This can work. And okay, iterative computation and accumulator programming. Those are patterns or maybe techniques, whatever that means. But why are we naming them? That's I found it funny. Just when I wanted to mention that. I don't know. I haven't figured out the rule yet. Um,
I mean, if you think about it, iterative computation is a thing that's normally named if you're doing imperative programming, right? They're called loops instead.
but that's the thing. If we, like people don't use this nomenclature, you see. Like when we are writing a function, then we want to make its tail call optimized because we want to make we will need to add an accumulator to make the last call tail call. We don't say, hey man, oh yeah, Friday nights, right? They are great. Instead of of having a happy hour, I'm doing accumulator programming. Nobody says that. Like, what are we doing? Uh, so like that's weird. But anyway, again, I'm not saying this should not be written. I'm not saying this should not be in here. It should definitely be in here. It's just that the act of naming things that are usually not named or referenced by that name is weird. That's the only thing that I want to mention. So this is very classic stuff, like iterative computation. Like, come on. Aside from the syntax, has anybody ever not seen this before? Like, come on.
Yeah, this is basically a while loop.
Uh,
Rather, actually, this is an until loop because it keeps going until you hit a condition, right? But it's basically the same thing.
yeah. So this is essentially a while or until loop. But this is a general schema. We're gonna fill the holes as we go. One moment. Recording. Okay. So pause aside. This is a general schema. You were about to say something, right, Marie?
Uh,
Sorry.
Not really. I mentioned that this is an until loop, which is basically like a while loop, but with a not in the condition.
Yeah, general. This is a general schema for a while loop or an until loop. Then we have an example of the square root. and then how can fit an example into that general schema. And then there is trade-offs about putting things inside, like making local functions or making them outside. Uh, yeah, I think this section is pretty interesting. I just don't like the conclusion because I think 3.8 is the final version
Yeah.
of what they chose to go for. But we don't talk about what is the cost of redefining a function every time. We don't talk
The
about that.
cost the cost is you need to capture all of the free variables of the function, right? You
Oh
don't
yeah,
really need you don't really need to re-emit the code for the function, but you do need to capture all of the free variables, which in this case, some of these don't have any actually.
yeah, but I think we should have talked about that. Like, if we're talking about this level of detail, I think we should have talked about the costs. But well, that's just being nitpicky. And then from general schema to control abstraction, this is the general. Um, yeah, a while
And
loop.
then, and then it's the classic, yeah, just make it an argument, basically, right?
Transform.
Yeah, is done, transform, and
Oh yeah, you need to receive that as an argument. That makes total sense. And then we finally go to recursive computation. And then it's saying that recursion is more general than the iterative computation because it can actually do more. The recursive function can call itself anywhere in the body and can call itself more than once. And then we talk about recursion in two levels, the recursion happening in the data types and recursion happening on functions. A very interesting detail that the book points out is that usually the function that is handling a particular recursive data structure mimics, like there's some resemblance between how the data structure is defined and how the function that interacts with it looks. And that's
yep,
obvious for anybody that did any sort of programming in their lives. Uh, but sometimes you don't notice obvious things. So it's good that you
yeah,
pointed out. Very good that you pointed out. And then we have the example of the factorial, and then we're gonna go talk about. It's always like this. Oh, this is nice. Like it works, but it's not efficient. So let's try to make it efficient. And then oh, okay, what's the problem? The problem is that the stack is growing. Oh my God, memory is not cheap anymore. No, I'm kidding. Uh, the implications of this the stack growing are not actually just memory consumption. It's actually speed as well. And then we have an example, well, a demonstration on why the stack grows. And then we go to the substitution-based abstract machine, which is essentially cheating. So instead of having the differentiation between identifiers and
and
variables, we're gonna
variables.
just gonna unify all of them in a single shot because why not?
Mostly because actually using the proper abstract machine by hand is kind of bothersome.
Yeah, this
So
is
it's
just for
like,
humans.
yeah, this is just for humans, basically.
And then what we're gonna do, and this is a very common operation, by the way. So we have a recursive definition of something, and we see that it sucks performance-wise. So how can we make it better? Easy. We One of the ways is changing it to an iterative computation version of the function.
In this case, using algebra.
Yeah, in this case, using algebra. But you will see a pattern here. So now, and this is very common, like very common. You're writing a function that has a particular interface, but the version of the function that you want to write has usually an extra argument. So I have to create a local one and call it in here.
Yeah,
And then he decided to call it fact eater. A lot of like I've seen Haskell code calling these go, just go function. And usually the go functions like that, they are just the real function with the extra arguments, and that you're calling on the body of the real one.
and usually you call the function only once and with a particular set of arguments, right?
No, you call it
So,
twice.
oh
But
no, 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 I
that's
mean in the outer function, right?
okay.
Not the recursive call. And if that's the case, then actually, like if you're coming from scheme or closure, you probably know loop recur or named lets. Those are basically the same thing,
Hmm.
but with a nicer syntax.
And then now this is the summary of this last portion. Well, that's pretty huge section, but it's 3.4 essentially. So we're going to define recursive data types such as list. We're going to extract a pattern, call it accumulator programming. And then we're going to talk about different lists, which I was not accustomed to. Um, and I'm still not accustomed to, so I'm not comfortable with some of the rewrite functions that you're going to write. They're going to be more efficient because they're using different lists. Then we're going to go to a queue and then a tree, and then we're going to see a parser and
Tree drawing.
tree drawing. Okay, so the first thing is the list. So this is pretty easy stuff, right? So a list is either something with more lists or nothing. And then we just say, okay, we actually want to put to say what is the type of that. So okay, let's put a type variable in there and call it a day. And then we also, well, this is just an example of a binary tree. We're gonna see
Binary
trees
tree.
later.
Yeah.
This is just for to have the introduction of a signature. Um, and then we have limits of notation. Yeah, so this is talking about, oh, we don't have dependent types. Too bad. Um, and
Yeah.
then programming with lists. Yeah, so thinking recursively, converting recursive to iterative programs, correctness of iterative computations. Yeah, so this is something that this book also introduces. We are trying to prove things, maybe not formally speaking, but at least informally speaking.
Yeah. Try to reason out if what you're doing is actually correct, right? Which you
Um,
should be doing if you're
but
programming.
it's more than just because the verb reason, like when you say, well, we are reasoning about it. That's a very vague verb. We usually don't say that actually we're doing induction. We're not usually when you say reasoning, we're not using dedicated techniques. Usually, you're
Well,
just
yeah.
reasoning. But these folks, they go a little bit further than that. They go, okay, we are gonna try to use some established methodology to do it.
Well, yeah, it makes sense because like it just follows. Like if you're into mathematics at all, you probably notice that yeah, if you have a recursive data type, most of the proofs about it will be inductive. Like it's just a fact of life.
Yeah. Um. Yeah. So this is the beginning of what we're talking about. So think recursively. We think of a base case and we think of a recursive case. And then we have, and this is very common, right? So every time we're talking about recursion, we're usually talking about these two, at least these two guys. We have example of the length. This is the type signature. Then we have an append function. This is the type signature. And then we have some properties. This is actually another thing that is interesting about this book. It also attempts to make you interested in establishing properties because in some languages you actually have to prove the properties sometimes,
Yeah.
right? But in here we don't. But at least it's being mentioned here that append new m actually equals m. Again, that's kind of obvious. This is a very obvious property that you can just say.
Um,
But it's interesting that this is being brought up, and we don't have to. OS doesn't require us to establish these things, but we are doing that, and I like that because I think that's the right path to follow. So you're trying to think as your function as something more than just. It's more
it's
special
more
than just like a function that, like in C.
it's more than just a program that you wrote for your computer to run. It's actually a mathematical operation with properties, right?
Yeah, exactly. We are trying to put more emphasis on trying to say, okay, what are the details about this guy? Okay, it has this time complexity, it has this size complexity, it has this set of properties, this is the base case, this is the recursive case. Like, we're trying to list a bunch of things that are important about this function.
By the way, can I just say this definition of append is actually deceptively beautiful because it's actually tail recursive.
Because it's tail recursive.
Yeah, because of how the list construction in the recursive case desugars into a tail call.
Oh no, but that's not okay. That's because of the sugaring of this, not because of
Yeah,
what is written. Because the way that it's written, the cons is actually in tail call. But we saw
yeah,
this
no,
last time.
yeah, we saw this last time.
We
This
saw
actually
this last
turns
time.
into, yeah, this actually puts append in a tail position, which
Yeah,
is nice.
yeah. Okay, more properties about append. So yeah, this is pretty obvious. If you append new with an M, the answer is M. This is not being what's the
Well,
name?
those are the. This is not being.
Co. It's with C. Commutative. So it could have done also M new equals M.
Yeah, that particular property. Yeah, new is an identity on both sides of the operation. That's correct. It's it's not mentioned in the other case, but that case is not being used in the definition of the function, which is the point that it's making here, right?
Yeah. And then okay, and this is also very interesting. Convergence analysis. Convergence analysis. One of the reasons that I imagine new people into programming are afraid of recursion is precisely because they can't tell that. You make a function and you're not sure if it's going to terminate for important cases. Well, we're not proving it, but this is a very good hint that if things are getting smaller, sometimes it's not trivial to say if things are getting smaller. Okay, I know that
Yeah.
myself. Sometimes you need math to decide to make the decision of that judgment. But this one is not one of them. So you can literally see that because we are destructuring something and LR is smaller than this, we're going to terminate this. Um, okay, so then we have, yeah, so this is dynamic typing again. So, oh, what if you're trying to send something to a function that is not the correct data type? Well, that's that's on you. So you have to write that. Um,
Yeah.
usually with an else. So this
Well,
is not a list, blah blah blah. Go on.
in this case, it's actually just going to throw an exception, right? Because you're pattern matching. You only listed cases for lists. So if you pass this something that's not a proper list, it's just gonna break.
Yeah, nothing too new there. Um, yeah, naive definitions are often slow. So this is the reverse definition of.
Yeah, this is a very cursed reverse implementation.
Well, I wouldn't say cursed at all. Computers are fast, but this is definitely not the best. Not the best. And then it's going to explain why, because this is actually in square. The set grows in the input size length, defines recursive computation that is an iterative. And then converting recursive to iterative computations. So how the heck do we do that? Interesting. So the way to do that is actually adding an accumulator to it. That's how we do it.
Yep.
And then we're going to pick, okay, so just for simplification, right? So this is a length function. And in here, we're going to grow the stack because we need to compute this in order to compute the answer of this, and so on and so forth. How do we fix that? Easy. We just do the sum in here and pass it along. And because of the tail call, because of the last call optimization, this is gonna be constant in stack size anyway. And then
And
that's
then you
all I
have to
do.
fill in the I with a zero,
Yeah, yeah.
right?
You need. That's what I said before. Usually, you're gonna have to define that as an internal function. Inside the function that you're gonna actually be making it public for everybody else to use. And then you call just that with whatever initial value your commutator requires. In this case, 0. Um, we can use the same technique for length, right? So we just keep reverting the thing as we do a cons, right? So we
Yeah.
start with an empty list, and then you grab the answer and you keep doing cons on the heads of the list that we are reverting, and then that's it. And then
Yep.
this is what I'm talking about. This is state invariance, right? The idea is to define
Yep.
a property of the state that you can prove is always true. It is a state invariant. If P is chosen well, then the correctness of the computation follows. And then we have a triple equals in here. That's fancy. Then we first prove for the base case, and then assuming this is on the final stage, prove. Yeah, this is induction essentially. And then we're gonna prove that P holds for Si plus one, and if that's the case, we say that it holds for P as I.
Yep.
Um, the difficult step is, in this proof is to choose the property P. It has to satisfy two constraints. First, it has to combine the arguments of the iterative computation such that the result does not change as the computation progresses. Second, it has to be strong enough that the correctness follows from P as final. A rule of thumb for finding a good P is to execute the program by hand in a few small cases, and from them to picture what the general intermediate case is. That's bad, because this is essentially saying, you're gonna figure it out. Just trust me. Just write a few times. You're gonna see it. I have faith in you. And as someone that is really, really, really bad at this, and I know this for a fact, I don't think this helps me at all. I don't think this helps me at all. So I'm very frustrated about having a hard time doing these type of proofs myself. And the only thing that I can tell you to help you is, brother, you're gonna have to do some practice, because that's not obvious to me. That's not like, oh, just write a few cases. It's gonna be obvious to you. It's gonna be a piece of cake. That's usually not how that goes.
Hmm.
And then we have the parallel between writing the data type that is recursive and writing the recursive function that handles it.
Yep.
And then we can mess around with more advanced nested list types, and the recursive function follows. Well, it doesn't follow exactly bit by bit, because now we have a guard in here instead of having another case of pattern matching. But this is just to show that the way that you structure the data types actually influence how we're going to handle them in the functions.
Yep.
And then we have these predicates here, and then we have another version of length L. Well, this is actually just a skeleton. We're filling the gaps. And then we have another definition on that, and that changes how we do this, because now we have one less case to handle. The one using the guard disappeared.
Yep.
And it's subtle, right? Because if you take a look, this is saying nested, nested, T nested. And this is saying nested, nested, T. There is missing another nested in here, and that may allow us to simplify this function, which is fine. And then we're going to see a more advanced example of this thing with this, which is the merge sort.
Sorting. Very nice.
And look at this, man. Remember the trick of, oh, you want to pattern match multiple things at once and you don't want
Just
them to be nested? Just use a
just put them
tuple.
in a tuple. Yeah.
Yeah, even the
Just put
book
them in a
acknowledges that this
tuple.
is a clever trick. Like, man, it's just clever. It's just what it is. Because it's really, really boring and bad and unreadable when you have to nest them, especially if they are repetitive. So this is pretty good. And what are we doing here? We're saying, well, these are the base cases, and then, oh, let's just see which one is. Well, merge sort. Do I have to explain this? You have two things. You go one by one matching and see which one is smaller, and you keep doing that.
The fact that it's using a less than instead of a less than or equal kind of bothers me because this is actually not stable, but oh well.
That's fair. Um, and this is what we're doing,
Oh,
right? So we start by that, and then we go through multiple other states of the state machine until we're finished.
Yeah, this is actually for something that's a bit later in the page. It's not about merge sort at all.
It's not about merge sort at all. Are you sure about that?
Yeah, that's control flow with threaded state, right? It's about.
It
I think
seems
it's
like
actually on
this
the.
image is that close related to this image, you know?
No, that second image is actually related to another program that we will see in a bit.
Okay, I thought this was related to that in my memory, but well. Then I have the split function because you have to split the things. And then we combine the two things, the merge and the split, and then we have merge sort. And then we have the freaking accumulator.
Yeah, that picture is about this procedure, actually.
Yeah, so introducing accumulator. So state S is represented by adding a pair of arguments, S1 and Sn, to each procedure. This pair is called an accumulator. This represents an input state and Sn represents an output state. So we keep going until we reach the base case, and then we just do that. Well, because this is a procedure, which means that this is an output, given that this is informing us that Sn is the output.
Yep.
By state threading, we mean that each procedure's output is the next procedure's input. So essentially, like again, a state machine, a state monad, whatever. But right now, the technique of threading a state through nested procedures is called accumulator programming.
This has different names in different places. Like in Racket, if you look at the How to Design Programs books, both the first and the second edition, they actually refer to this as world passing style because it's a function that takes the state of the world and returns a new state of the world, right?
Yeah, no, this makes perfect sense. Yeah, so as you can see, this is the output. Oh, the input of the next one. This is the output. Uh, this actually reminds me of Jai's context programming. Uh, so um, let me find it. Well, let's actually go to the part where he talks about 24 arguments. That's where I need to bring up the Jai's context.
Yeah,
Mut
multiple accumulators.
Yeah, so consider the following procedures: takes an expression containing identifiers, integers, and additions, translates the expression to machine code for a simple stack, and calculates the number of instructions. We don't need to go over this. The fact that of the matter is that this is doing accumulating two things in the single threading, I'd say.
Yep.
And then yeah, the Acros Polar compiler was written in this style. Which style? Writing having a lot of accumulators to accumulate different things. And you may say, well, combine them in a single record. But that's essentially the same thing. It's just more convenient to write that. But then you're gonna have a gigantic blob, such as in Lyceum's game. We have a gigantic state, and we keep passing that around for everybody. It's not exactly the same as in here because declarative programming assumes immutability in some sense. In Lyceum we have a mutable state, so it's a little bit different. But when I read this means 24 additional arguments, I immediately remembered the Jai's context. So let me try to find it.
Uh, I don't know much about Jai's notion of context, but from what you told me and from what little I saw, I think this might be related to dynamic scoping actually. Dynamic binding specifically.
Dynamic binding. Yeah. So essentially, I found these two posts earlier. When looking at the game programming on system level languages, control over memory allocation becomes very important. This is why new C in C++ has placement new operator. Rust has its zoo of memory management tools, and C's memory allocator is just a function. Similarly, new system level languages like Zig proudly claims that it has no default allocator, and you are encouraged to decide which allocator you want. But this is annoying because, well, you have your allocator. Are you gonna keep passing that around, that bastard, everywhere? This breaks the whole function signature, even though the internal working of the function shouldn't affect it. This in turn makes libraries also have to decide between breaking the existing public interface or cheat by picking some allocator. And for the latter, well, then suddenly that you can pick an allocator promise does not really work. Not to mention that an extra allocator parameters pollutes the function profiles unless your language supports some kind of default parameter values. And the way that Jai gets around this problem is by introducing something called context, which, well, I don't have the compiler, I don't have examples, I'm not in a beta, but what I understand is that the context is some sort of binding that every function has access to, and probably in the bootstrap of the program you can put stuff in there, or maybe everywhere you can put stuff in there. Why not? Um,
A new context can be pushed, changing the operational context for a duration. Yeah, that sounds a little bit like dynamic binding, actually.
yeah. In Jai, the context is there to guide different parts of your program to use whatever services you desire. The default context comes with good defaults, but you can change them as needed. Among these are the allocated, the temporary allocated, the logger, the assertion failure callback, formatting options for print, runtime error logging options, and so on. You can also access your current thread index through the context. But wait, there's more. If for whatever reason it makes sense for your program to have additional context, you can add it yourself. And why is this important for game development? Because what I imagine, I'm not a game developer myself, so I'm just speculating at this point. What I imagine is that they have a gigantic struct that holds the game state. And because it makes sense that most functions will have to poke that thing, instead of having a bunch of boilerplate of, okay, every first argument of all of these 80 functions will be the state, let's just have that implicit.
Modularity, essentially. You only need to mention it if you actually use it.
Exactly. So this is the first thing that when I read this, I was like, man, uh, is a grammar notation that is used to hide the explicit threading of accumulators.
Yeah, but DCG is not quite the same because it's
No, I'm not saying it's the same. I'm saying that
no,
I got reminded of that.
yeah, no, it serves a very similar purpose, but it's the way it's implemented is very different. As it mentioned, it's just a preprocessor, right?
Mm-hmm. Uh, we no longer program in this style. We find a programming with explicit states simpler and more efficient. It is reasonable to use a few accumulators in the declarative program. It is actually quite rare that a declarative program does not need a few. An AND merge starts with accumulator, so that's what it is. 13 minutes. Okay, and then we finally reach different lists. Difference
Difference
lists.
lists, yeah, those are really nice actually, but unfortunately they actually require data flow variables.
Require data flow variables.
Yeah, otherwise it's not really useful at all.
That doesn't sound like it's true, because the append that we're gonna introduce here, well, can you do this without data flow variables? Probably, but you would have to do some sort of.
The point is that it wouldn't be efficient, right? The whole point of using this is that, oh, actually you can do append efficiently even though you're using a linked list, right?
But that's the lie. You are not using a linked list. You're using true. And they have a very special property, which is difference structures. A difference
They
structure is a
share,
pair of two partial values where the second value is embedded in the first. That's
yeah,
why those are the two hiccups that this thing requires alongside data flow variables to be as awesome as it is.
yeah, basically the list on the right needs to be a tail of the list on the left.
Yeah. So for example, yeah. So to append this, okay, so this is a tuple. Again, we are cheating here because you're gonna think it's a single list, but internally it's not. So this is a tuple of two lists where we have x on both sides. And if you want to append uh, this with this, we just say that x is equal to the first list of the second. What does this do?
Constant time append, basically.
No, no, yes, but make like more in detail. We are saying we're gonna say that x is equal to this, so this is gonna appear on the left hand side here, such as this, right?
And then we take the right hand side of the
Yeah,
second list
and then you take the
to
right hand side of the second list.
maintain the tail as it was
Yeah,
on the
so
right.
essentially append is an equals. It is an equals of data flow variables. So it's not a normal equals. Uh, but yes, it is pretty magical. And it's pretty interesting. I never seen that before. So that's great.
Funnily enough, you might actually be able to implement this in Clojure, though the interface wouldn't be nearly as nice as it is here.
Yeah, that's what I was thinking. I think that if you don't have data flow variables,
But
I don't know
Clojure,
about the convenience and the notation.
yeah, Clojure has promises, which semantically are kind of like data flow variables, but you can't just replace a variable. You can't just put a value in a variable in a place that expects a value and make it work, right? Because the promise in Clojure is a separate type. I mean,
Uh, yeah, yeah, that makes sense. Yeah, so apparently this is the basis of many advanced Prolog programming techniques, which is why I am very uneducated because I'm not educated in Prolog as I should be. And a difference list lives somewhere between the concept of a value and the concept of state. It has good properties of a value. Programs using them are declarative, but it also has some part of a state because it can append once in constant time. This is a really weird association, in my opinion. Why does it make sense to say that it has a power of state if it can append once in constant time? What does one have to do with each other?
well,
I have no idea.
Well, it's basically exploiting the fact that data flow variable is a very restricted form of state, right? Because you can set it once. That's all you can do.
Ah, okay, I see. I see. Okay. And you go through another example, flattening a nested list. And nothing too crazy about this. I would recommend like reading this very carefully because when I was reading this, it twisted my brain. Okay, that I was hungry. I didn't have. I hadn't have lunch back then. But this can be understood. This can be understood. Even I understood. So everybody can understand. So yeah, just be careful, bit by bit. It's gonna make sense eventually. I promise.
And then we flatten difference lists, which is, well,
Yeah,
it's a bit more involved, but it's also a lot more efficient,
yeah,
potentially.
yeah. No, the whole thing about this is that we are making things that are moderately naively inefficient. So like, if you think about it, man, how am I gonna do append better than linear? Like, uh, the answer is twofold. If you have the correct data structure alongside more expressive constructs, such as data flow variables, you can actually open a lot of gates. Like you did because this what? Look at this. This is essentially a show off. Like, oh, you guys are doing linear or quadratic. Fuck you. I can do in constant. Why not? Um, yeah, it took me a lot of time to understand what the heck was going on with this. Because at first, this doesn't really make a lot of sense, especially because there's no hashtag in this code. So you ask yourself, where the heck is the difference list? Difference list. And the answer is that it's treating these two guys as a difference list. So I think we should go over the reverse at least.
All right.
So what does this does? We want to reverse something. Cool. The answer is going to be y1. Cool. So this is the output, and it's marked as an output. We're going to use an auxiliary list, which is going to call y, and s is the input. And then check, oh, but let's actually skip the base case. So we
Yeah,
want,
the base case is trivial.
well, it's not because of this. Um, but this is the known the not the base case. So we have something in there. What do we do? Fine. We say that the y is actually going to be the current y and the current x, but this is going to be the new y on the next iteration. So what are we doing? We are putting things. We are putting things. In, we're doing a cons on the beginning, right? This is the
Yep.
accumulator until we're doing things. Um, so we keep accumulating, accumulating, putting things on the head. So we are destructuring a list and putting things back at the head. So this is essentially reversing it.
Yep.
And then when we're done, we say, oh, actually the answer points to y. And then you have to remember that at this point, y has the answer.
Yep.
Y has the answer.
Y has the answer.
Uh, so yeah, it took me a while to read this. I was very hungry at the time, so maybe that was part of the reason. And then we have, oh man, again, 5 minutes to go. We still have queues, trees, and examples. Okay, so what is a queue? A queue, it's FIFO, right? So first in, first out behavior. And
Yep.
we insert on one end and we delete on the other end. And then this is a naive implementation of a but last. So Haskell's last function is probably like this as well. But of course, we want this to be in constant time. But as it says in here, in a strict functional programming language, the declarative model without data for variables, we can only achieve amortized constant time operations.
Um, you could potentially. Can you actually achieve a true constant time in the worst case? Probably not, right?
Well, I haven't read the reference, so I can't say. I'm just trusting the author. But in here, we can actually have real constant time. And then we say that the queue is ephemeral. And ephemeral, what does that mean?
Each version exists from the moment it is created to the moment it can no longer be used. It's right afterwards.
From the moment it is created to... Oh, this is because of how the different lists work.
Yeah, because once you bind a variable, that's it. You cannot rebind it, right?
Yeah, once you pick that unbound data flow variable and you bind it to something, you're done. Okay, so this is how they do it. And at first, I was extremely confused by this definition. Because this is the amortized version. So this is what essentially like... Is this the guy from the...
Yeah, purely functional data
Yeah.
structures.
The guy from the infamous blog. Yeah, I was confused. Why the heck do we need check for anything? But at some point it made sense because you're
It's
saying
in the
that
delete.
F is the front and R is the back, and at some point we need to put things from the back to the front.
Yeah, this is basically representing a queue as a pair of lists, right? And they are linked lists, which means you add things to the front of the list, but then you can't really read them in the order that you inserted, so you need to do a reverse there somewhere. And that's
Yeah,
what the check is doing.
yeah, we're gonna have a cost of a reverse from time to time, and the cost will happen when the front is empty. We're gonna have to pay. Yeah, so worst case constant time ephemeral queue. Yeah, so this is the chat version. And why is this weird? Because if you take a look at it, we are inserting to this queue this x, and then we say, hey, do you have something in there? I just noticed this case is not exhaustive. Oh, because this is always be true. No, okay, never
Yeah,
mind. We have a queue in there, and then we say E1, which is gonna be, well, unbound,
yeah,
but we're gonna say that E, which is something that is in the queue already. This is the back, right? Because this is the size, this is the front, and this is the back. We're gonna say that the back is equals to the element, and then putting the unbound thing in there, and then we increase the size and put the new variable in there. We put the new variable in there.
Yeah, the tail here is always an unbound variable, basically.
Yeah.
The back of the queue, I mean.
Yeah, but how do you read it? That we don't have like a get from the queue in here. So I'm actually pretty curious because you have as
You
your new reference something that is unbound.
Well, that's because it needs to be unbound so you can do the next insert, right?
No, I understand. This E1 is going to be the new E on the next insertion, and then it's going to go here.
The trick is that S and E together form a difference list if you put them in a pair.
No, yeah, it's mentioned that in here. So I guess before printing, you're going to have to append them.
Before printing, what do you mean?
Well, if I want to get elements from the queue,
You just take the S, take the head of the S, and that's your element.
take the S, take the head of the S, and that's your element.
Yeah, S is like the front of the queue, but it's actually also just a list. Except the tail is a free variable most of the time.
But now I have yeah, like I said, I'm not very well versed with data flow variables. So let me ask you them questions. So in this particular case where I'm inserting something, this is the current back, right? This is the current second list, right?
Yes,
And then we are saying that this is equal to a cons between the element that we want to insert and an unbound variable, right?
yes,
And then we put that unbound variable in here. What are we doing with
yes.
these equals exactly?
The trick here is that you see what the new queue does?
Yes, it says that the size is 0 and we have two unbound variables x's in there.
Yes, that means that the value in the middle of the queue will actually have the element added to it at the end, well, at the current end. But then we move the variable that points to the end to be a free variable, this E1 that you just declared here.
Yes, I understand that.
But but you will note that the value in the value in the middle, the S there, stays the same, right?
Yes,
But it was originally bound to be equal to the E when the queue was initialized, right?
yes,
That means that it's actually those two elements, I guess, are connected because when you
yes.
create the queue originally, they were the same,
Wait a
and
moment
then
then.
when you
So
do an insert,
you're saying that this is x e1, right?
yeah, this may have more stuff than just the X, but when you do the very first insert, yes, it is.
Well, let's do another insert. So let's say that we have already an x e1. Like, yeah, we already have done this before. So now I'm adding another element in there.
Yeah, in that case, the let's call the second X X1, I guess, because let's be zero
Yes,
based. In that case, the S is going to be X E1 before the call, right?
yes,
Then inside of the call, you create a new E1, which we can call E2, I guess.
yes.
Um,
And
you're
e1
going to
equals x e2.
uh, you're gonna do yeah E1 equals X E2. But
Yes.
remember, E1 was actually the tail of.
Ah, I
You see?
see, I see. I see what's going on. Man, yeah, that's what I said to the people at work. If you think about these as pointers, it actually helps.
It does. It's like you have a pointer at the very tail of the list, right?
Yeah, but
That
this is
you can
this
use it to
is
do and you can use it to write exactly once.
this is high level pointer arithmetic.
Yeah,
Very high level because
it's declarative pointer arithmetic.
like we're not doing sums or subtractions. We're just going equality and the runtime does the rest. Okay. Yeah. Yeah, but that's what I said. When you read this type of shit, like here about the flatten, you need to be very slow and probably pick a piece of paper and understand what the heck is going on, precisely because of this reason. And it gets crazier because of this example here. Um, where it is? Where is it?
Uh,
Doing such a delete returns an unbound variable that will be bound to the corresponding inserted element. With this first definition, maintaining multiple. No, that's not it. Where is the thing? Yeah. No, that's not it. Yeah, here. We can delete an element before it is inserted.
yes, we can.
That's crazy.
It
Like,
is, but it also makes sense.
we can delete the element before it is inserted. What the heck is going on? Um Doing such a delete returns an unbound variable that will be bound to the corresponding inserted element. Um, oh, this happens when when you delete something, you get an unbound variable, and then you can pick that variable and insert it later. But then when the equals comes, it's gonna just disappear, I guess. Man, that's so weird. So weird. Uh, yeah, so this is an example of like both Q3 or Q4 are calculated from their common ancestor Q2. Q3 contains Peter and Paul. So let's see why. So in here, Peter, and then P3 adds Paul on top of the Q2, and then Q4 adds on Q2 Mary. Yeah, so you can have multiple versions of the. We're talking about multiple versions, right, of the Q
Yeah.
simultaneously. And then we'll go to persistent queues. And then a queue that supports multiple simultaneous versions is called persistent.
Yeah, if you watch any Rich Hickey talk about implementing closure, he mentions persistent data structures a lot because they are actually very important.
Now, because this is what allows us to pass a queue or a data structure to a function, and when the function doesn't mess around with a copied queue from that elsewhere.
Yeah, basically, the core idea is okay, you want to be able, those structures are like, they are supposed to be treated immutably, right? So you should be able to share the same structure
Yeah,
in a
but we
bunch
are
of
kind of
places.
like if you think about it, the data flow variables are kind of adding mutability to them, in a way.
Yes, it's a very restricted form of mutability, but they kind of are, yes.
Yeah, so that's very interesting to think about. We have to create persistent data structures because even when they are declarative, they have some degree of mutability.
Yeah, it's a very restricted, very well behaved form of mutability, but it still is mutability. You can't use it to implement state, but it is a form of mutability.
Yeah, so this is what we were talking about doing the bind of the tail. So when you do that, you're done. And then we need to do some fresh copies for you, and then you can do the forks that you may desire. And then they are now not interacting with each other.
Yep.
And then we finally go to trees. And then we have a sketch of a tree. We have binary trees. We also have the notion of balanced tree. And then we have ordered binary trees. It's actually pretty interesting that the author decided to go with ordered binary trees before going to binary trees.
Uh, I
So
mean,
for those that forgot, ordered binary trees are the ones that have the properties of the root is greater than the subtree on the left, but is smaller than the subtree of the right on the right. And this comes with a penalty of balancing the tree.
yeah, you need to balance the tree.
And well, we're gonna see that in the deletion operation anyway. So anyway, so
I mean, you would have to balance the tree anyways in order to maintain good performance, right?
no, of course, but I really don't like those trees because of the balancing process, especially because I had to implement them myself. Um,
Okay.
so lookup on the tree, very easy to do. We also have a more readable version of that. Um, nothing too crazy. Insertion of that, and then deletion. And then the deletion is like wrong. This is actually not doing that. Why? Because um,
Because it's
it's
removing
not
the
doing
entire
this.
subtree. Yeah, it's not doing that.
Well, here actually. So if you have stuff that are not leaves, you are nuking everything below it. They're not leaves. Yeah.
Yeah.
And for some reason, random reason, some people call it percolating. I don't even know what this verb means, but well. And what we need to do, we need to preserve it. We need to do an inspection on the subtrees. And if we have something that is on the leaf, we need to do something about it. And then that requires us to have removed the smallest of the T2 or the greatest of T1. And there we go, the implementation of that. And this is a very interesting way to describe it. The difficulty occurs because another tree satisfies a global condition, namely being ordered. Many kinds of trees are defined by global conditions. Algorithms for those trees are complex because they have to maintain the global condition. In addition, tree algorithms are harder to write than list algorithms because the recursion has to combine results from several smaller problems, not just one. So that's a very
Yep.
interesting property, that it seems that lists are well behaved even in smaller scopes. But trees, you have problems on smaller scopes, but you also have problems on global scope. So that's very interesting to think about. And then we go to traversals, classic, depth first, breadth first. And there we go. So BFS. And it talks about using a queue to see which ones you already have iterated upon, I believe.
Yeah, that's the breadth first.
No, but he also says that you can do the depth first with one of those, but by replacing a queue with a stack, which is clever.
Which is, well, you can, but why would you do that when you already have the call stack, right?
No, but that's the thing. We are doing a swapsies, right? We are, oh, I don't want to use the memory from this region anymore. I actually want to use this region.
Okay, that's fair.
So
Well,
it's
yeah,
like,
in that case, that's actually a nice way to contrast the two approaches. Like, if you look at the actual bodies of the two traversals, they're basically the same. The only difference is one uses a queue and the other uses a stack.
I don't know if I will go that far to say that they are the same.
I suppose
Um,
technically the order that they do things, well, that's the whole point, right? The order is different, but like the bodies,
the bodies are different.
they wouldn't be if you had an explicit stack. I guess that's the point.
I think they are anyway. So if you look at the DFS accumulator body and you look at the BFS, they are very different from each other. Very different.
Mm,
But maybe we have a DFS. Nope. Yeah, this is the BFS with accumulator. Yeah, they are different. Very different. Oh no,
explicit
wait. This
stack.
is the version with the explicit stack.
Yeah.
Okay, now you're right. But instead of doing an if, it's doing a pattern matching. Uh, yeah, then it talks about the memory use of those things, and then we finally go to the examples. So we have drawing trees, which has a very neat trick that I want to use at some point in my life, which is to embed the coordinates of the drawing into the process. Because when you think about drawing, especially nested data structures, what you think is about spacing. So you do some sort of trick about, okay, the spacing is this, let's multiply that by some sort of like what level I'm in the tree, and then let's multiply that, and then sum how distant am I from the leftmost guy, and all of those things.
Right.
Here, we are actually embedding coordinates off the panel of the browse display thing. We are embedding that in here. So like, I never thought about doing it like that. And the reason is because you are polluting your data structure with things that are only related to display. So that
Right.
sounds like a sus choice. But I guess if your whole entire goal is to print it, then just, well, go for it. We
I
might as
mean,
well.
it's you're doing it for display, explicitly for display anyways, right? So it actually makes sense to put display data in it.
Yeah. And then we have how you're gonna do that, and then we have adjoin, which is essentially this is cursed. This thing is cursed. The fact that you can at runtime change the definition of a record, that's cursed.
This is basically like merging maps in Clojure. It's basically the same thing, except it's for records in Oz instead of maps in Clojure.
Down passed arguments are sometimes called inherited arguments, and upward passed arguments are sometimes called synthesized arguments. I never heard synthesized arguments before. And we are talking about the one that is talking about upwards is
It's the return value, basically.
yeah. Yeah, why not return arguments, output arguments, synthesized? Like what kind of worm in the brain we have in here?
I see you're enjoying that book.
I finished it.
That's very nice.
Anyway, then we have the parsing. We're not gonna go over this too much, but it's essentially the place book, textbook definition of okay, you have a Saturday afternoon and you are a nerd, you should do this.
Let's implement a parser. Why not?
Yeah, so we have non-terminal symbols and terminal symbols, and we're gonna create an abstract syntax tree, which by the way, this uses a nomenclature that is not yet used in the book, and I don't know if I forgot about it. I did a grep and couldn't find it. What the heck is a factor?
Factor?
Yeah, where the heck is it?
Uh,
Here. Factors and identifiers are parsed as follows.
Factors. I think that's from the grammar that it's parsing, no?
Well, it is. But what the heck are those?
Well, if you look at the.
It's in here. Yeah, here.
Well, it's a factor, as in. It's a multiplication factor, as in. This is a language for arithmetic.
Ah, weird naming choice. Um, yeah, and
I
why
mean,
are
the
we
order
talking
of.
about parsers and drawing trees? Because they use trees. A parser outputs an abstract syntax tree. And there's even a very interesting, I didn't know about it. It's abstract because it's encoded as a data structure in the language and no longer in terms of tokens. That also seems like worm in the brain. I have no
No, it
idea
isn't.
why
No, it isn't,
abstract
because.
means this.
Oh, it isn't, because there's also a notion of a concrete syntax tree, which does have information relating to the original stream of tokens.
Well, I guess the reason that this makes sense is because the concrete is the one that actually makes sense. It's because one is the opposite of the other,
Yeah.
and then abstract came naturally as the antagonist, I guess. Well, anyway, uh, yeah, and then he talks about ambiguous grammars, which well, we're not gonna go to talk about that right now. Um,
And then 3.5 is next session.
yeah, so I'm gonna finish the recording.